All right. Hey, let's try another video solution. Here's from chapter 6, number 12. It's this one that I just sent out the second half of the question. The question, sadly, when it was scanned, it missed a piece. I apologize for that. But hopefully you got my email. And then I sent the one from the wrong edition, and so I fixed it now. Okay, but let's just try to work through this problem. It says here that a tennis ball of mass 0.2 kilograms is thrown against a brick wall. So this tennis ball, it's heading towards this brick wall. It is traveling horizontally at 12 meters per second just before hitting the wall and rebounds. So I'm going to just kind of do that drawing. So now it has rebound off the wall. So now it's heading this way at 8 meters per second. Still traveling, and then this is where it ends. So let me switch over to, where would that be? What I just sent you. How did it say? Still traveling horizontally. All right, so we don't have to worry about one dimension. It just comes in and goes out. The ball is in contact, so I'll call it delta t. It's in contact with the wall for 0.04 seconds. What is the magnitude of the average force on the wall? On the ball, which is from the wall. So Newton's third law, they're equal and opposite. All right, so the force is, on average, the change in momentum over the time taken. So this would be final momentum minus initial momentum divided by the time taken. Okay, now maybe I'll do a little more here. The final momentum, this is after the rebound, would be its mass times its final velocity. And then it would be before the rebound, it would be mass times its initial velocity. And we have all these numbers, so now we can just plug it in and see what kind of number we come up with. All right, so let's take the mass of 0.2 with a final speed of. Now, the final speed is going to the left, so let me call it a negative 8 meters per second. Now, be careful with that negative. Because I could have drawn the picture the other direction, and so then it wouldn't really, this would be a positive instead of a negative. So the actual sign there isn't so important, okay? So it kind of depends on how the author writes it. In fact, let me switch over to the solution here. Yeah, he writes it with a negative speed, although he puts the negative out here. Okay, so he's got the same picture in his mind. Then we've got minus the 0.2 kilograms and the initial speed. Now the initial speed is the 12 meters per second. That's the to the right, and again, that could have been a negative if I had drawn it going towards a brick wall that way, and so that would be a negative, and that would be a positive. So the magnitude would still be the same. It'd just be the wall would be pushing in a different direction, so the sign would be different. So the actual sign isn't too important for this problem. Now maybe I should put kilograms above the mass because I forgot to write that, and then that's all divided by the 0.04 seconds. So grabbing a calculator here, I guess I would have 0.2 times a negative 8. And then I would subtract a 0.2 times a 12. And so that is a minus 4. Divide it by 0.04. And I get a negative 100. And if you look at the units, kilogram meters per second each second, that's the definition of a Newton. So this would say that the force on the ball would be 100 newtons, and the negative means it'd be over here towards the left. And sure enough, that's what you need to make a ball ricochet that way. And like I said, had I drawn the brick wall over here and the initial was this way, these signs would be opposite. This would come out to be a positive, which would make sense because the wall would be pushing in a positive direction. All right. Hope that helps.